We've talked about how to do stress transformations using the basic equations, but there's another way that we can do this using a graphical method called Mohr's circle. So Mohr's circle is the graphical way we can illustrate a stress transformation. Essentially what we're going to do is we're going to be drawing a stress versus stress, so our normal stress versus shear stress, plotting a circle based on the elements that were given in a stress element, plotting a couple of points, finding the center of the circle, the radius, and then being able to pull off some values from this circle. So it creates a really easy visual representation to help us find some of those things rather than using really big, long equations. There's nothing wrong with using the equations, but it can be a little bit easier to see and understand where these values are coming from, where those equations are coming from, when we use this circle to kind of explain everything. And it is a little bit convoluted. It takes a little bit of getting used to actually learn the circle, but it can be a really powerful tool to represent any transformation you want. Instead of having to plug things in over and over and over again for every single little transformation you want to do, you can see all of the transformations at once. So it can be a super powerful tool for finding principal stresses, angles of rotation, maximum shear stresses, all of those things that we've talked about using equations to do, we can use this little circle graph to do. And the easiest way to explain how to do this is kind of walking you through a step-by-step example. So that's what we'll do. We'll have an example up top, and I'll write the steps on the side as we're doing them, but we'll work through an example together so you can see how to construct this circle. All right, so let's talk through how to build Mohr's circle together using this stress element as an example. As you can see, they want us to find a bunch of different stuff for it. We want to find the average normal stress, principal stresses, max shear stress, the angle theta of the principal stresses, and then for part E, we want to find out what are sigma x prime, sigma y prime, and the shear stress when rotated 23 degrees clockwise. So here's our element over here. I'm going to walk through the procedure on the left side over here and then draw in the circle in kind of our main area, talking through each bit for this specific problem. Every single one of these graphs is going to be built for the specific problem. So our first thing that we're going to want to do is we want to draw our coordinate system in. And this can be harder than you think it is. It sounds easy on its surface, but when we draw this coordinate system, the key thing with the coordinate system is that our sigma value, our normal stress, is our x-axis, and it is positive going to the right, right? So it's the x-axis, positive going to the right. That's standard convention. But for our shear stress, our positive value is down. So counterclockwise is down. And what I mean by that is when I draw in the coordinate system here, and so I have an x-axis and a y-axis that are sigma and tau. My normal stress sigma is positive going towards the right, but tau is positive going down. So my positive shear stress is down in this lower quadrant as opposed to being this up portion. So it's really, really key to remember. Otherwise, all of your signs are going to come out backwards for everything. So we set up our coordinate system, our normal stress on the x-axis, the shear stress on our y, positive to the right, and positive downwards. And the reason that we care about that is because we're going to go ahead and plot the values that they give us in this element on our chart here. So we have, let's see, we have sigma x is 45 megapascals, sigma y is negative 60 megapascals, pushing inwards, and the shear stress is 30 megapascals. So what we're going to do is look at the combination on each face and plot those points. So I'm looking for the points for my X face. So for my X face here, what I'm seeing is I have a positive 45 on my sigma. So if I go ahead and do, you know, let's maybe do it in tens. So 10, 20, 30, 40, 50. So 45 would fall halfway between here. And I'm going to give myself some notches in these other directions that may or may not be helpful because I'm freehanding this, and so it's not going to be very exact. It's a lot more helpful when you have some graph paper, or, you know, just an engineering calculator is good too. So I've got some notches on here. I'm going to plot my first point. We said 45 in the positive sigma direction, and then 30. This 30 is causing a counterclockwise rotation of the element, right? If we think about the way that the shear stress is pushing the square, the shear stress on this X face is pushing it counterclockwise, right? It would be causing a counterclockwise rotation. And counterclockwise is positive. This is counterclockwise is positive. You can also think of this as this top tau is clockwise. So if counterclockwise is positive, that means I'm going down by 30. So I'm at 45, and then right here, this point is 45, 30. Both positive values. It's in the positive quadrant. So 45 and 30. And then I can plot my other one. Right, so my other portion here, now I'm looking at sigma y. Sigma y is negative 60. So I'm in the negative sigma direction, right? 1, 2, 3, 4, 5, 60. But my 30, you'll notice the 30 megapascals of shear stress is causing clockwise rotation. It's causing a clockwise rotation on the y face here. So what that means is that this point is actually going to be 1, 2, 3, about right here. Right, so I have 2 points. This is negative 60, negative 30. 2 points that are going to be 2 points on my circle. So the next thing that I want to do is I want to connect the dots, right? Because if I connect the dots, I can find the center. Because these are just on 2 edges of my circle. So if I go through and I connect them, just draw a straight line. Maybe I can use the line tool. That might be that. Oh, that's pretty cool. All right. I use the line tool and I connect those dots together. And this is going to tell me where my center is, right? So my center between these guys, the center always, 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 say it with me, always falls on the sigma axis, right? It's always going to intersect the sigma axis. This one, my notches aren't perfect, so it doesn't exactly look like it, but the center of the circle is actually right here. Right, these my spacing is a little bit far out on this side. But the steps we've covered so far, so we set up the coordinate system. We plotted, so we plot the stresses. So we plotted 2 points, the x and tau and the sigma y and tau. So we plotted those. 3 is connect the dots to find the center. All right, so the center of my circle here is going to be this pink dot. It always, always, always is on the sigma axis. And it falls halfway between these points, halfway between the 2 sigmas that I have. So if I were to average them out, I've got the 60, negative 60 on this side and the 45 on this side. I can find what that average is, which I'm going to do because my graph doesn't look perfect. You could, if you have a nice, beautiful, perfect graph, read it off of your graph. But mine is a little hard to see. So I'm just looking for the halfway point. So that's going to be negative 60 plus 45 over 2. And that gives me 7.5. So this point hits at 0. Or sorry, 7.5. 7.5 comma 0. No shear stress. Just sigma at our center there. So fun fact, this might look familiar from our equation video because this is sigma average. The center of your circle is sigma average, right? It's the average normal stress. So we've already, not even having a full circle here, we've already found one of the answers to our first problem here, right? Part A asks us to find the average normal stress, and we've done it now. It is 7.5, or negative 7.5. Sorry, it's on the other side of the x-axis. It is negative 7.5 megapascals. Boom, done. So the center, right? So in step 3, the center is the average normal stress. So it's very exciting that we can find an answer without even having drawn a circle. But now we will go ahead and we will draw that circle. I'm going to move that over there. Let's see, what other fancy tools you got? Paint. Can I draw a circle? Oh, okay. I'm sorry, that's just not how I thought the circle tool was gonna work. I think I was expecting it to work how SolidWorks does. Oh, I hate this. Okay. I just wanted a circle. Alright, that's about, I mean, that's a circle, basically. But what I would do if I were you is I would use maybe a piece of string and a pencil to go around that center, right? Put your string on the center there and then use your pencil as kind of like a compass. You could use an actual compass if you have one. I know they're not, as common in this day and age. You could also just plot this on an online circle plotter. I'm sure there are ones that exist where if you give it a center and a side point, they'll make you a nice circle. So any of those options that are available to you, I would use any of those, or just even, roughing it in with a ruler as I was going through and sketching these in my notes. I was just using a ruler and marking a notch and then just moving that ruler and marking little notches until I had a circle. So many ways you can go about actually creating this circle. A digital one is going to be the easiest in terms of pulling numbers off of that you need. But for an exam or something, I would recommend a compass or a protractor or some way to kind of sketch out this circle where you get a pretty good idea of the circle. All right, which is step 4, by the way. Step 4 is draw the circle. All right, so we've done that now. Draw the circle. All right, so it's centered on that negative 7.50, and it goes out to those 2 edge points. Now that we have a circle here, what we're going to do is find the radius of this circle. So to find my radius of the circle, right, I'm coming out from the center. I can just follow this line up to the point that I have because I know that coordinate and I can find these side lengths here, right? So I know that since this is set on 0 and it goes up to negative 30, I know this distance is 30. And I can find this distance because it's going to be that difference between 60 and negative 7.5. So if I do that subtraction, I get this length of 52.5. So, oh, look at that. It's a nice little right triangle. I can use trig to find out what this radius r is. Right? I can find this, I can use this tangent, or inverse tangent of 30 over 52.5 gives me the radius of my circle there. And that is number 5. Once you draw the circle, you want to find the radius. Because this radius has all kinds of helpful information for me. Did I find the angle? I did. This is the angle. That's not the right equation. I'm sorry. This is... okay. For some reason I found this angle, which is not what I wanted to do. Maybe it'll be helpful later, but this is an angle. Whoops. Sorry, I want to use Pythagorean theorem to find the radius. So radius is going to be the square root of 30 squared plus 52.5 squared. This gives me angle theta. Let's back burner that. I don't know if we need that. We must need that, I assume, at some point. Whoops, took a chunk of the circle with me. That's all right. We'll just, you know what, maybe we should just leave things alone. Let's just leave everything alone and pretend like everything is fine. Okay, so now I can find my radius using Pythagorean theorem, which is the thing I was actually supposed to do. And I get a radius value when I plug that in the calculator of 60.5, about. That's rounded a little bit, but about 60.5 is the radius that I get. And that radius is going to be super, super helpful to me because what I can get with the radius are the principal stresses and the maximum shear stress. I can get all of my maximums by just knowing this radius, right? Because my maximum principal stress, those happen at the outer corners. Let's use a different color. At the outer portions of my circle here on sigma, right? So sigma 1 and sigma 2 are my most farthest out points. So to find these, I can just add the radius to the center and they'll give me sigma 1 and sigma 2, my two principal stresses. Let's make a little bit more room here. Bring this down. So we can, once we find the radius, sigma 1 is going to be our center plus the radius, and sigma 2 is going to be the center minus the radius. And then our maximum shear stress, that happens at the top of the circle, right? So if I go right above the center there to the top of the circle, this distance is again just r. It's just r since it's centered on the sigma axis, right? Our circle is centered on that x-axis. This distance, r, is the same as our max shear stress. R is just the maximum shear stress. So that's perfect. That finds like two other things in our thing up here, right? Part B and C, the principal stresses and the max shear stress, we can now get just because we know the radius. So our max shear stress, it's the radius, 60.5 megapascals. Our principal shear stresses are going to be the center plus the radius and the center minus the radius. So center is at negative 7.5. So negative 7.5, and then I'm going to add the 60.5. Gives me 53 megapascals. And then for sigma 2, it's the center minus the radius, right? Give us this distance here. So negative 7.5 minus 60.5 gives me negative 68 megapascals. So those are parts B and C, right? So this is B, this one is C. We found A. A was negative 7.5. That was our average shear stress. So there's just a couple more things we want to do. Right, we want to find, for part D, we want to find the angle of the principal stress. And then for E, we want to find, hey, if we rotate this thing, what are the new values? What are the new values for our normal stresses and shear stresses for the element? So what we're going to do is find that angle next. All right, we're going to go ahead and find that angle next. And oops, I did already do it. This is where this tangent comes into play, right? This 30 and this 52.5, if I look at this angle here, this angle that I've found represents, I'm going to call it phi, actually. That's why I'm erasing it. I'm going to call this angle phi. And it's the same angle on this other side over here. Right, so this is angle phi. And as you can see, we've swiped down from our sigma axis, swiped down by this amount phi. So this inverse tangent of 30 over 52.5 gives me an angle of 29.5 degrees. But the key thing here with Mohr's circle is that this angle is not theta. This angle is actually 2 theta. So phi is 2 times theta. And that's the same 2 theta that we see in all of those equations, right? So Mohr's circle is on a different coordinate system because if you can see our principal stresses, sigma 1 and sigma 2, they're 180 degrees from each other on the circle. But on our stress element, they're only 90 degrees apart, right? So everything is doubled on our Mohr's circle. So instead of using this 29.5, that's the angle that we're seeing here, but it's actually half of that. So the angle theta that it's being rotated through is half of 29.5, which is 14.9 degrees. 14.9 degrees. And that's because if we swung this back up to where the principal stress is, that's really the difference between where our element is sitting right now. Right? So our element is sitting here on this line right now. If we moved it up by 14.9 degrees, we would get this principal stress 1. So that's our sigma, or sorry, our theta p, the angle of that principal stress. And again, we can go back and check all of these values with the equations if we wanted to make sure that we're doing everything right. But everything here, we're just pulling off of this circle, right? We're constructing the circle and finding different little pieces of it to find all of our answers, really. All right, so that was our 6th step. Step 6 was find the angle phi. And then, I'll put a star, I guess. Note that phi on our circle is 2 times theta. Right, 2 theta, that's what we saw in the equations. 2 theta, all the angles are doubled on our circle versus what they are on the element. And then for our very last step, the only thing that we haven't solved through this example is where it says, hey, if I rotate this by 23 degrees clockwise, what's my new thing? So I can find any angle of rotation just by taking, let me take a line here. Right, I can find any new angle of rotation, taking a line and passing it through the center. I can find any endpoint, right? I can rotate this line anywhere that I want. As long as it goes through the center, I can find the points that I need, and I can figure out what that sigma x prime, sigma y prime, the tau xy prime, all of those values I can find just using this circle. So that's what we're going to do. We're going to, ooh, that's cool. Sorry, it's apparently my first time using Microsoft Paint. I've never played with any of these tools. I'm always just writing stuff. All right, what color was it? There we go. So your last step here is find any new angle of rotation of interest. So For any new angle of interest, how do I want to put this? For any rotation angle, need just a little bit more room. Pi circle. For any rotation angle, add the new angle. Add the new angle to your existing one. Add new angle. Draw a line. And calculate new stresses. Stresses using trig. Right, so we're just going to be pulling trig off of this circle. That's going to be our final step for any rotations that we're going to do. So looking back at our circle here, what do we have going on? What are we doing? We're going to rotate this 23 degrees clockwise. Right, so 23 degrees clockwise, that is a theta. 23 degrees clockwise is a theta. Do this all in yellow, I think. It's nice bright. Theta is 23 degrees. And we know that phi is double theta. So actually the angle that's getting put into our circle here is going to be 46 degrees. So we're adding 46 degrees onto this existing line. And it's going clockwise. So it's pushing this line out 46 more degrees. So let's say, this is where a protractor would be very helpful. I don't think Microsoft Paint has one of those, so I'm just going to wing it. But we will, where's my, I just want to grab this line. How do I grab this line? I probably should have learned how Paint works before I, started clicking on things. All right, that's not the button that I wanted. That's okay. We'll just draw in a new line. I'll put it in white here. So we're going to draw in a new line where this pushes out by 46 degrees. And we get some line that goes through the center. Maybe looks like something like that. Right? Touches both ends, pushed down by 46, goes through the center here. Goes through that center there. Whoopsie. Undo. Oh my god. Anyways, all right, so we've got our 46 degrees. It's being pushed out this way. So what we're going to find from this new location, right, from this new location, what we can find is that this distance to the center, so I've got new distances here. Here's to the center. I come down and I can make myself some triangles here, right? So I can find this angle that my triangles are making, and then this distance x and y are going to give me what I need to find sigma x prime, sigma y prime, and that new shear stress. So this angle, what did we say? We had phi here was 29.5, and then we pushed it clockwise by 46 degrees. So 29.5 plus 46 gave us an angle of 75.7 degrees. So if I subtract that out, well, I guess I don't need to. We can use this angle here if we want. All right, so this angle here is going to be 75.7 degrees. That full angle of rotation that it's going through. If you wanted to, you could find the smaller angle, just do 90 minus that 75.7. That's what I was going to say earlier. You don't necessarily need to, but it is 14.3. 14.3, that angle there. If I find these x and y values, This is our key thing, right? We have the hypotenuse. The hypotenuse of our triangle is the radius, right? It keeps coming back. That radius is going to be really helpful to us. We have the angle, so we can find the x and y values. So those x and y values give us the locations of x prime, or sigma x prime and sigma y prime. Right, so our sigma y prime is this distance here, right, from our axis out to the point. So if I add my center to this x value, I'm going to get sigma y prime. If I add my center to this value, this x value, I get sigma x prime. And my circles become a little bit crowded here. But these are giving my new stresses based on where they're located at the circle. So if I find this x value, x is going to be, I know the radius is my hypotenuse, I have that angle there, so my x is going to be 60.5 sine 14.3 gives 14.9. And then this y value here, this y value right here, this height right here, that's going to give me the shear stress at that point. The y is going to be the radius cosine 14.3 equals, let's see, when I punch that in the calculator, I get 58.5. 58.5 for that shear stress. So what I'm going to do is I'm going to add my center, which is negative 7.5, to this plus or minus, right? So whether I'm going positive or negative direction, to this x value, and that's going to give me sigma x prime and sigma y prime. So sigma x prime is going to be that value, this distance, right? This distance right here, plus the center distance. That tells me sigma y prime. And same deal down here. The center minus that radius. So here I have a center minus radius is negative 7.5 minus 14.9. And that gives me, this plus minus for y prime, c minus r, negative 7.5 minus 14.9. This gives me 7.39, 7.4. Yeah, 7.4 megapascals. My bottom one is negative 22.4 megapascals. And then we said the shear stress was just the y value. So it's literally just this 58.5. So those are my elements. This is the trickiest part of all of it with this rotation, that you have to find these new values. But this is it, right? So if I were to draw in my new element so that it's been rotated down, rotated clockwise by 23 degrees, what I would see is I would see my x value, sigma x prime, 7.4 megapascals. I would see that my y is negative 22.4 megapascals, negative shear stress, compressing that. And then, or negative normal stress, and then my shear stress is positive. That's 58.5 megapascals. I rotated that element. So it takes some practice, it takes some work, it takes a lot of graphing and maneuvering things. But if you can maneuver it all, you can really read off everything you need without having to punch in an equation 1,000 times. Right? Here it's basically just trigonometry that you're using over and over again rather than memorizing an equation. Let's take a look at another example. Now we're just finding the principal stresses, max shear stress, and the average normal stress of this element given. So if we look at this guy that we're given over here, we have a normal stress in the x direction of negative 12 ksi. And notice I have no normal stress in the y direction. Absolutely nothing going on there, so that's 0. And a shear stress in the negative direction, right? Looking at the x side, it's pointing down, negative 6 ksi. So if I want to build myself a Mohr circle to find the principal stress, max shear stress, and average normal stress, what I'm going to do first is I'm going to come through and make my coordinate system. Right, remember our shear points down, clockwise shear points downwards. And I'm going to plot the points that I know. So I know, let's see, I know that when my x is negative 12, my shear is going to be negative 6. So I'm up in this upper left quadrant. I go negative 12 and 6. Let's say it's this point here. Negative 12 and 6. Graph paper helps tremendously with things like this. And then if I look at my y side, I have a, oops, that's a negative. Sorry. I have a no y, right? So 0, I'm going to be sitting on my axis here. And it's being pushed counterclockwise, so that's a positive shear. 0, but a positive 6 puts me right there. Right, so that's going to be 0, 6. And if I connect those two guys, I can find my center, which falls halfway, like right between those guys, right? My center, it's not the button I wanted, but that's fine. My center is going to be at 0, or at 6, 0, right? Negative 6, 0. Let me just rewrite all of that. Negative 6, 0, right? Halfway between 12 and 0, halfway between 6 and negative 6 gives you negative 6, 0 is my center. And as we know from our example problem, that's going to be our normal stress, right? The average normal stress is the center point of the circle. Negative 6 ksi. Boom, done. I didn't need any equations or anything. I just was able to find it even without a circle here. So I can go in and I can put myself a circle. It's like a pretty good circle. There we go. Now we're cooking. That's a circle, all right. I've got a circle in here and I need to get my principal stresses and max shear stress. So we know that the max shear stress and principal stresses are given by the radius. So if I go ahead and find the radius here, I can do that by constructing a triangle. Right, so this distance here between negative 12 and 6 is 6. This distance between 0 and negative 6 is 6. So perfect. I've got a nice little triangle in here. I can find my radius is the square root of 6 squared plus 6 squared, which is 8.49. 8.49 is my radius, which will give me my max shear stress, right? Same on top and bottom. Max shear stress as well as the principal stresses, right? They're all one radius away from the center. So my max shear stress is exactly the same. Right, max shear stress is exactly the same as the radius. So max shear stress is going to be 8.49 KSI. And then my principal stresses are just the center with the radius added on and subtracted off. Right, so I'm going to take my center for sigma 1, that's going to be -6 plus 4 or 8.49 gives me 2.49 KSI. And my other principal stress is the center minus that radius. 8.49 gives me -14.49 KSI. Right? And that's it. Those are all of the things that it asked for. Those are all of the things that I needed. Those are my answers. All I did was a little bit of trig and a little bit of circle constructing, but to me, it's a little bit clearer to do it this way than doing some random equation where I don't really understand where things are coming from. It's really easy to make a sign mistake in your random equations. So Mohr circle can really help you pull things out really fast, especially if you're doing a lot of problems with the same element setup. It can be easier to set up a circle, more worth your time to set up Mohr circle than to just repeatedly plug things into equations. All right, so we've got one last example that we'll take a look at here, which asks us to represent the state of stress on this element if it's rotated 30 degrees counterclockwise from the position shown. So we have an angle of rotation, we have our little element over here, where x is -8 KSI, our sigma y is a +12 KSI, and our shear is going to be a -6 KSI. All right, so we're going to go ahead and take those and plot them out on our circle. Positive sigma in the right direction, positive tau in the downwards direction. So we're going to use this to plot our points. Again, we're plotting our points. We look at the x side, and then we look at the y side. So for our x side here, I'm going to plot these points. It's going to be -8. Let me give myself some more check marks. 1, 2, 3, 4, 5, 6, 7, 8, 9. Myself some of these. Try to kind of stay on a coordinate system. Oh, that's going to be a little bit off, but that's okay. All right. Try to keep myself a little bit on track there. But we've got -8 in the sigma direction. So -8, 1, 2, 3, 4, 5, 6, 7, 8. And then a -6, right? Looking at that x side, shear stress is negative. So 1, 2, 3, 4, 5, 6. Just about there. -8, -6. And then I'll look at the y side here, where I have a counterclockwise shear. So that's a positive shear and a positive y value. So up at 12. 3, 6, 9, let's call that 12. And down by 6. It's right about there. I might have not drawn this big enough, but that is okay. This one is a +12, 6. And then our next step is to go through and connect those points so that we can find where our center is. You can see that my dashes are a little bit off because I know that my center should be hitting at 2. Right? My center should be halfway between -8 and 12, so 12. -8 plus 12 is going to be 4, and then half of that, right? It's halfway between the two, should be 2. So I've got a center at 2, 0. That's where my center is, and then I can come in and draw my circle. Again, my circle's a little bit off the charts. It's a little bigger than what I intended to have, but that is okay. There is my circle. So I plotted my points. I found the center of the circle. Next thing we're going to do is find our radius, right? That's our next step. So our radius here, I construct a little triangle. I get this distance here is -8 plus 2. This full distance is going to be 10. 2, it's moving over 2 and then moving over 8, so that's 10. And then this height we can see is 6, has a value of 6. So I can come in here and find my radius from Pythagorean theorem. The radius is going to be the square root of 6 squared plus 10 squared. Punch that in the calculator, I get 11.66. Radius of 11.66. Okay, so that's all fine and dandy. The reason that I need to find all of these things is because what I really want to do is I really want to find the angle here, and I want to do some rotations, right? So I want to find what this angle is that I'm operating in. So this angle right here, phi. And phi is going to be that same 6/10. It's the same on both sides, right? This distance is also 10. This distance is also 6. So I can do inverse tangent of 6/10 to find that angle there and find out that that is a 31-degree angle. A 31-degree angle, and that has pushed this way. So we have our phi here, and what we want to do is we want to rotate this thing 30 degrees counterclockwise. 30 degrees counterclockwise. Remember that that is a theta value, and that theta theta equals phi. So in order to get the phi that I'm moving, right, this is a new angle that I'm moving through, I need to multiply this by 2. So I am moving my angle by 60 degrees and I'm moving it counterclockwise, right, moving it counterclockwise. So here I have my phi. I'm moving this, I'll go ahead and draw it on this side. So this was my original angle. I am moving this whole line counterclockwise. Counterclockwise. You could draw it from either side, right? Counterclockwise. I'm moving through 60 degrees. Moving through 60 degrees. So I'm traveling across those 31 degrees, and then I'm going the rest of the 60. So this new line that I have, all right, that needs to go through the center. There we go. Now it goes through the center. That new line, this new rectangle or new triangle that I have, that I create here, get a fatter marker. Where is, I know the line thickness is here somewhere. Okay, well I know it is, I just don't know where it is, I guess. Is that not it? Okay, that's fine. I'll just draw really, really bold. Alright, so I get this new triangle here, where I had 31 degrees here, and then I pushed counterclockwise by 60 degrees, making this angle here 29 degrees. So this angle is 29 degrees, and what I want to find is I want to find the sides of this so that I can find my new sigma x prime, sigma y prime, and the new shear stress for this new state, right? Because we said I can use this along with this radius value that I know, 11.66. I can use this triangle that I've found to find those stresses. All right, so here's my x value of this triangle. Here's my y value of this triangle. I'm going to go ahead and calculate those. So x is going to be 11.66 cosine 29, which is 10.2. And then y is going to be 11.66 sine of 29, which is 5.65. So again, what I can do with this x and y here, right, is that my x, sigma x prime value, looking at my circle here, my sigma x prime value is given by the center plus that x value. The center plus that x value. So that this point that I'm hitting on this graph, right, because I'm looking at really at the points on the circle, but they match up to the points right here. Right? This value is my sigma x prime and my sigma y prime. These values here. When I add and subtract from the center this distance x to the center, sigma x prime is going to be 2, that's the value of my center, 2 minus 10.2, which is negative 8.2 ksi, and sigma y prime is going to be 2 plus 10.2, 12.2 ksi. And then again, my shear stress value, this distance here, is just y. Right, the location that this is hitting on this axis, it's just the same as the y value. So tau x prime y prime, 5.65 ksi. So that's it. Those are my answers for this one. And I could go ahead and do that relocating for any given angle on this circle. So it takes a little bit of work, it takes a little bit of practice, but it's really great to have two options available to you, both the equation method and the graphical method, that you can use both to check your work, right? We love having different ways to check ourselves to make sure that our answers are working out right. So it's really good to have this in your toolbox so that you can check yourself, right? You can see if your graphing is matching up with the equation.